Hi everyone. In this lesson, we're going to learn how to classify real numbers. So in this box here, I have an example of real numbers. And this is just a small list of real numbers. Real numbers are any numbers that you can think of to solve math problems. But like I said, this is a small list. -8, 1, 0, 4.6, -5.4, and so on, just to give you an idea. Now, real numbers are divided up into two main groups, the rational number set and the irrational number set. If a number is irrational, it cannot belong to the rational number set. If a number is rational, it cannot belong to the irrational number set. So they don't overlap or intersect. However, this set itself can be divided up into other smaller groups, okay, that make up the integer set and the whole number set. And there's also the natural number set. We're not going to talk about that one. We're going to focus specifically on the whole numbers, integers, and rational numbers that make up this set, and we'll talk about irrational numbers. All right, so let's specifically talk about those subsets that make up the rational number set. So whole numbers are a subset of the rational number set. They are positive numbers that have no decimal part. So I'll show you. 0 begins with 0, 1, 2, 3, and I can't list all of the numbers because the list goes on infinitely. So I'll just put dot, dot, dot to show you it goes on in this direction forever. Okay, so all those numbers are considered whole numbers. The integer number set, which is also a subset of the rational number set, they are all the whole numbers that we have here, 0, 1, 2, 3, dot, 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 and they're opposite. So we go in the opposite direction. -1, -2, -3, dot, 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 to include all those numbers. And integers have no decimal parts. Just remember that. Just like whole numbers have no decimal parts. So if I asked you if 7.5 is an integer, your answer should be no, because you see how it's 7.5. This is a decimal part, so this is not an integer. However, if I just said 7, that would be an integer. Okay, no decimal parts. Okay, integers have no decimal parts. Let's go on to the rational number itself, okay? The definition of a rational number is any number that is written in the form of a over b, where a is an integer, b is an integer, and b is never 0. Okay, so here's an example. 7 over 12. That's a rational number because this is an integer, a is an integer, and b is an integer. That's a rational number. 9 over 35. That's also a rational number because this is an integer and this is an integer. It's in the form of a over b. 17 over 0. This is not a rational number because b cannot be 0, remember? So this is not a rational number. All right, and there's lots and lots of examples, but these are just two examples, okay, to start with. Now let's talk about the irrational number set. The irrational number set are numbers that do not repeat, they do not repeat, and they do not terminate. So here's an example. 4.732469843072 dot, dot, dot. It goes on and on forever. And you see, we don't have a repeating decimal here. There's no repeating decimal. We just keep getting different digits each time, okay? Here's another example, pi. is irrational. Or here's another example, pi over 15. That's irrational because a is irrational to begin with. Okay? All right, on the next page, we're going to name all the sets each number belongs to. But the first thing we're going to go over is the letter that we're going to use that represents each number set. So the letter that we use to represent the whole number set is W. For integers, we use Z. For rational number, we use Q. And for irrational numbers, we use P. These are not my selection. These are the letters that mathematicians have decided to use for these number sets. Okay, so now let's name each subset each number belongs to. 8. Well, 8 is a whole number. Remember, whole numbers begin with 0, 1, 2, 3, ... So 8, it belongs to this set, so it is a whole number set. So it belongs to the whole number set. It's also an integer because remember, integers are the whole numbers and their opposites, the opposite. Okay, so it is also an integer. Is it rational? Well, you can take the number 8 and turn it into a fraction. It doesn't change its value. It's still 8, but it does meet the definition of a rational number because you have a fraction where a is an integer and b is an integer. So it's also rational. All right, let's go to number 2, negative 15. Well, it's not a whole number because whole numbers are not negatives, but it is an integer because remember, integer are all those whole numbers and their opposites. Okay, So yes, it's an integer. Is it rational? Yes, because we can easily convert that to a fraction, negative 15 over 1, which meets that definition, a over b. So it's also a rational number. Okay, 13 over 25, well, it's not an integer because this is actually a decimal part because the numerator is smaller than the denominator. If this was 25 over 25, it would be 1 whole, but it's less than 1 whole because the numerator is smaller. So we know this is a decimal part. So it is not an integer, it's not a whole number, but it does meet the definition a over b, so this is rational. 0, well, 0 is part of the whole number set. You see that here? So it's a whole number. It's also part of the integer set. Remember, the whole numbers and their opposite make up the integer set, so it's an integer. And it's also rational because you can take 0 divided by 1. It doesn't change its value, but it does meet the definition of rational number, a over b. So it is also rational. All right, so the next one, the first thing we want to do is see if we can convert that to a fraction. Well, 0.25, is that the same thing as 1/4? So this is a rational number because 0.25 is 1/4, so it is rational. It is not an integer because it is a decimal part. It's less than 1. It's less than whole. And it's not a whole number either. Okay, let's go on to number 6. Well, number 6 is the same thing as 3 over 4. So it is a rational number. It is not an integer because it's a decimal part. It's not a whole number for the same reason it's a decimal part. All right, 1.3 is certainly not an integer because it has this decimal part right here. But 1.3 is the same thing as 1 over 3/10. I'm sorry, 1 and 3/10, which gives us a mixed number, but this mixed number can be turned into a fraction, improper fraction that is. 10 times 1 is 10 plus 3, so that's the same thing as 13 over 10, where a is an integer, b is an integer, so this is rational. Okay, same thing is true about number 8. This is a mixed number. Okay, this is the same thing as 5 times 6 is 30. This is the same thing as 33 over 5, where a is an integer and b is an integer, so it is rational. Same thing for number 7, it is rational because this is the same thing as 12.8, okay, which is the terminating decimals. So all terminating decimals, you have a terminating decimal here, you have a terminating decimal here, all terminating decimals are rational. This is also a terminating decimal. We can convert that to a decimal, and that would be a terminating decimal. All right, let's convert that to a fraction first. That's the same thing as 9/10. This is a terminating decimal, by the way, which equals to 9/10, which is a rational number. -19, well, that's not a whole number because the whole number set doesn't have any negatives, but the integer set does have the negatives. Remember, it's the whole numbers and their opposites, so it is an integer. Now, can we turn this integer into a fraction? If we can, then it's also rational. It is -19 over 1 is the same thing as -19, so that makes it rational. Okay, let's go on to number 10, 23. It is a whole number, belongs to this set. And it is an integer because it belongs to this set. It's in here. So it's a whole number, it's an integer, and it can also be turned into a fraction, which gives us a rational number. All right, -16, it's not a whole number because we have no decimals in the whole number set. It is an integer because the integer set is all the whole numbers and their opposites. So this is an integer, and this integer can easily be turned into a fraction, which gives us a rational number. This is also an integer and a rational number. All right, so when you have square roots, first of all, you have to evaluate those. You have to simplify. So the square root of 36 is 6, and now you can classify. Well, 6 is a whole number, belongs to this set. It's also an integer, belongs to this set because it's all the whole numbers and their opposite. So it's an integer, it's a whole number, and it's rational because you can convert that to a fraction easily. All right, let's simplify square root of 25, which is 5. So that's a whole number, it's an integer, and it's rational because you can easily convert it to a fraction, 5 over 1. Simplify that, and you're going to get 7. So this is a whole number. It's also an integer and rational. Okay, this one here you can't simplify in your head like that because this is not a perfect square. So when you have a square root that isn't perfect, this is going to be irrational. So we're just going to say P for this one here. Same thing here. This is not a perfect square, so this is going to be irrational number. This is a perfect square, but it's negative, so it's -8. That's not a whole number because whole numbers don't have any negatives, but it is an integer. And it is rational because you can easily convert it to a fraction, -8 over 1. Negative square root of 81, we simplify that, it's -9. So it is an integer. It's not a whole number. It is an integer, and it's also rational because it easily converts to a fraction. Pi is irrational. Pi over 3 is irrational because it has pi. All right, so a number like this, you see, nothing repeats here. There's no repeating decimal here. You just keep coming up with new, different digits, okay? So this is a irrational number. P for irrational. This is a repeating decimal. This means 6, 4.444444, and it goes on and on and on forever. This is called a repeating decimal. All repeating decimals are rational. This is also a repeating decimal. This 13.2222. Okay, it goes on and on and on the same way. This is a rational number, so all repeating decimals are rational. This is not a repeating decimal. You see how the digits are different each time? And it goes on and on and on. It does not terminate. So this is irrational. So if a number is not a repeating number and it doesn't terminate, it is irrational. Okay, let's summarize that. Okay, so all terminating repeating decimals and fractions are rational. All non-repeating and non-terminating numbers are irrational. So here's some practice for you. Name all the subsets each number belongs to. All right, try these on your own. And this concludes this lesson on classifying real numbers.